Hello dear students. So today we will discuss about the modern periodic law and modern periodic classification. So as you know that since a long time ago people have been trying to classify the elements in different ways, whether it is the case of the process of classification by, you can say, Newland or Dobereiner triads, or it was the case of Manley's periodic classification. In every classification, the base of classification was considered to be the atomic masses. Earlier, whatever attempts have been made for classifying the elements, that were on the basis of their atomic masses. But there was a physicist named Henry Moseley. So Henry Moseley was studying the photoelectric effect of the metals. So while studying the photoelectric effect of the metals, he has seen that the frequency of emitted X-ray radiations, they depend on the atomic number of the elements, not atomic masses. Based on that, he has given a relationship that nu is equals to A into Z minus B whole square. What is nu here? Nu here is, you can say, is the frequency of emitted X-rays, and Z is the atomic number of the element, whereas A and B are the constants. So let me give you an idea about the photoelectric effect. So what is photoelectric effect? It is observed that when a metal surface is irradiated with the energy of certain minimum radiation, so because of which the electrons are ejected out from the surface of the metal, and that is known as photoelectric effect. So during this ejection, the X-rays that are emitted, the frequencies of emitted X-ray radiations, that depend upon the atomic number, not atomic masses. So based on this, Moseley could conclude that it is the atomic number which is more fundamental property rather than atomic mass. So based on this, he gave the law which is known as modern periodic law. So according to Moseley's modern periodic law, it is said that properties of elements are periodic functions of their atomic numbers. That means if you keep on arranging the elements in the order of increasing atomic numbers, then at certain regular interval the properties of these elements are repeated, or you observe a reoccurrence in their properties. And that was a major breakthrough in studying the classification of elements. And based on this periodic trend or periodic law, the table which we obtained is known as modern periodic table. So in this modern periodic table, if you look at the shape of the modern periodic table, it somewhat looks like this. That is the shape of modern periodic table. In this periodic table here, we have extreme left we have two groups 1 and 2, and then from here we have groups 3 to 12, and then we have groups from 13 to 18, and here at the bottom there are two series, the series that are known as lanthanides and actinides. So in this periodic table there are 18 vertical columns, and these 18 vertical columns are known as groups, and there are 7 horizontal rows known as periods. So here in this periodic table there are 18 vertical columns called groups, which are simple numbered as 1 to 18. And then there are 7 horizontal rows, and these 7 horizontal rows are known as periods, right? So that is a basic arrangement of elements in Moseley's periodic table, or you can say modern periodic table, which is also known as expanded or long form of periodic table. As soon as Moseley took atomic number to be the basic criteria for classification of elements, almost all the problems which were existing in earlier Mendeley's periodic table, they were all vanished, right? So if we look at the problems which were there in Mendeley's periodic table and how they could be overcome in this modern periodic table is, the first problem was putting the heavier elements prior to the lighter elements. As you can see in Mendeley's periodic table, if we talk about the elements like nickel and cobalt, the atomic mass of nickel is higher than that of cobalt. So in that way, as per Mendeley's arrangement, it was the cobalt which should have been kept earlier, and then that there should be nickel. But it was not like that, and that was an anomaly of Mendeley's periodic table. And that anomaly has been resolved here, because as the modern periodic table is based on atomic numbers, so atomic number of nickel is lesser than that of cobalt. So that problem is automatically solved without any confusion, right? The another problem was there in Mendeley's periodic table, that was there was no you can say certainty about the continuity of the periodic table, because Mendeley's periodic table was based on atomic masses, and atomic masses never increase in regular manner. It's not like that if one of the element is having atomic number 1, atomic mass 1, then another one must have atomic mass 2, and then another must have atomic mass 3, and so on. It's not like that. So if you find a gap between the two elements, you can't be assured whether these elements are not known, they will be discovered in the future, or the elements with such atomic masses do not really exist. So we can't say anything with surety about the continuity of the periodic table when it was the case of Mendeley's periodic table. Now in case of modern periodic table, that problem is also solved. Like as it is based on atomic numbers, and you know that atomic numbers always increase in a regular manner. Say if one element is having atomic number 1, another one must be having atomic number 2, then another must be having atomic number 3, as atomic numbers can never be fractional, because these atomic numbers are equal to the number of protons, and protons can never be fractional, right? So in that way, that problem of continuity is solved. And one another very major problem was cause of periodicity. So periodicity means repetition in properties of elements after regular intervals, right? So it was explained by Mendeley also that when we arrange the elements in the order of increasing atomic masses, then a repetition in their properties is observed after a regular interval, and this repetition in properties after regular interval, that is known as periodicity. But Mendeleev could not give any explanation to the cause of periodicity. He could not explain that if there was a repetition in properties, what is the cause of this repetition in properties, and that too was explained very well by Mendeleev's periodic classification. As you know that the modern periodic table is based on atomic numbers. So if we talk about atomic numbers, they decide the electronic configuration of elements. And these electronic configurations, they decide valency of elements, and valencies decide the properties of elements. So the problem is solved, that when elements are arranged in the order of increasing atomic number, then at regular intervals, the elements with similar valential electronic configurations are repeated. That's why they are having same valencies and they show same properties. Like if we talk about the elements of group 1 in the modern periodic table. So elements of group 1 here are lithium, sodium, potassium, rubidium, cesium and francium. So if we look at the electronic configuration of first few elements of this periodic this group, lithium is having atomic electronic configuration 2,1, sodium is having 2,8,1, potassium is having 2,8,8,1 and so on. So can you see anything common here? Yes, the common factors are the equal number of valence electrons. As they have equal number of valence electrons, they all have same valencies, and as they all have same valencies and hence similar properties. So the cause of periodicity, which was still now unexplained, could be very well explained on the basis of modern periodic table. So in modern periodic table, as elements are arranged in the order of increasing atomic numbers, so after regular intervals, the elements with similar outer shell electronic configurations are repeated. Similar outer shell electronic configurations mean similar valencies, and similar valencies mean similar properties. So that way you can see that modern periodic classification of elements was a very big achievement towards the study of elements, or you can say towards the classification of elements, right? So now if we look at the properties of elements, because here we are getting a regular trend in their properties, so we can look about the trends of properties of elements in the modern periodic table. And if we look in the trends in properties, what do you mean by trends in properties? If we talk about trends in properties, it means that while moving down the group or while going across the period, we observe a regular gradation in their properties. Either the properties are increasing down the group or they are increasing across the period, whatever is the case. So these regular changes that we observe in the properties of elements are known as their periodic trends. So the first very important property of the elements is their atomic size. So what is the atomic size? Of course, the property that lets you know that how big or how small is an atom. And as we consider the atoms to be spherical, the sizes of atoms are compared or measured in terms of their atomic radii. That is the one very important property which becomes the key factor of various other properties also. So if we talk about atomic radii, what is the atomic radius? It is the distance from the center of nucleus to the outermost occupied shell, right? So the distance from the center of nucleus to the outermost occupied shell, or you can say to the valence shell, is known as its atomic radius. Like say, if we talk about the atom having say three shells, so it is the nucleus here, it is the first shell, it is the second shell, and here we have the third shell. Say we are talking about the sodium atom having configuration 281, then in the nucleus of the sodium there are 11 protons, 12 neutrons, and in the first shell how many electrons are there? 2 electrons. In the second shell there are total 8 electrons, right? And in the outermost shell there is only 1 electron. So if we talk about the radius of sodium atom, it is a distance from the center of the nucleus to the outermost shell. This distance is known as, atomic radius, right? So before looking at the periodic trends of the atomic size, let's look the factors that decide atomic size. So you can say factors affecting atomic size or atomic radius. Here, so the first very important factor here is of course number of shells. So what do you think is the effect of number of shells on atomic radius? As you can see, more are the number of shells, farther is the outermost shell from the nucleus, and you can say bigger is the atomic radius of the atom. So here number of shells you can say is directly proportional to atomic radius. Like we have just discussed, say the example of lithium and sodium and potassium. In lithium there are only 2 shells, in sodium there are 3 shells, in potassium there are 4 shells. So as we move from lithium to potassium, as the number of shells are increasing, the atomic radius or atomic size is increasing, right? If we talk about another factor, that is the nuclear charge. Nuclear charge here represents the number of protons in the nucleus. Of course, more is the number of protons in the nucleus, stronger is the attractive force on the outermost electron, and these electrons will be very strongly attracted by the nucleus towards itself, and size of the atom will decrease. So here you can say that nuclear charge or number of protons is inversely proportional to atomic radius. More is the nuclear charge, smaller is the size of the atom. And then another factor which comes here is known as the shielding or screening effect. So what is shielding or screening effect? In order to understand this shielding or screening effect, let's concentrate on this sodium atom bag. If we look at the outermost electron of this sodium atom, this outermost electron of sodium atom is experiencing two types of forces. What are these two types of forces? The first one is the attractive force exerted by nucleus, right? More are the number of protons in the nucleus of an atom, stronger is the attractive force and smaller will be the size. Another force which this electron is experiencing is the repulsive force due to inner electrons. If this electron can be attracted by the protons present in the nucleus, at the same time the electrons present in the inner shells will also be exerting a repulsive force on the valence electron. And then in that case what will happen? That some of the attractive force of the nucleus will be counterbalanced by the repulsive force of the inner electrons. In that case we can say that the charge on the, or you can say the attractive force of nucleus on the valence electron has been reduced due to presence of the repulsive forces of inner electrons. And this is what which is known as screening or shielding effect. So what is screening or shielding effect? Now we can define it as to be the decrease in attractive force of nucleus on outer electrons due to repulsive force of inner electrons. So that decrease in attractive force is known as the you can say screening or shielding effect. So now here we can say that more is the screening or shielding effect, less is the effective nuclear charge, and bigger is the size of an atom. So from here we can conclude that more is the screening or shielding effect, less is the effective nuclear charge on valence electron, and bigger is the atomic size. Clear? So now keeping these factors in mind, now we can have an idea about the trends of, or you can say periodic trends of atomic size or atomic radius. So if we look at the trends, periodic trends, so let's first look down the group. see what are the factors working here when you proceed down the group in the periodic table. First of all, down the group, number of shells increase. And if number of shells increase, then what we expect that atomic size also increase, right? Then another factor that works is the number of inner electrons also increase. And if number of inner electrons increase, then again what will happen? The screening or shielding effect will increase, and again we expect the atomic size to increase. And the third factor here is, of course, the nuclear charge. Nuclear charge means number of protons in the nucleus. The nuclear charge here increase, and we expect that atomic size should now decrease. So see, there are two factors that are responsible for increase in atomic size, and there is one factor which is responsible for decrease in atomic size. And what we observe here is that there is an increase in atomic size of the atom. So that's why we say that when we proceed down the group in a group, you come from top to bottom, the atomic sizes are continuously increasing, right? And now we can look at the period. Till now we were discussing about the group, and now we would like to discuss across the period. So if we talk about across the period, see what are the factors here are. If we talk about number of shells, they remain same. If we move from left to right in the period, the number of shells in the atoms, they remain same. If we look at the number of inner electrons, that also remain same. There is no change in number of inner electrons, because in period when we move from left to right, one by one electrons are added, but these electrons are added in the same shell. No new shell is introduced here. And of course the third factor is nuclear charge. Nuclear charge means number of protons in the nucleus, and as we move from left to right, as atomic number is increasing, of course the nuclear charge is increasing. And you can see here the two factors that remain same, means almost having no effect on the size, and the only one deciding factor is increase in nuclear charge. So here we can say across the period atomic size increase due to increase in effective nuclear charge. So there is increase in effective nuclear charge across the period. That's why we observe a decrease in atomic size. As across the period atomic size decreases due to increase in effective nuclear charge. You have seen there are two factors that are not going to make any difference on atomic size. The only factor which is the nuclear charge, as this nuclear charge is increasing, and we have already seen that more is the nuclear charge, smaller is the atomic size. Across the period, atomic size decreases due to increase in effective nuclear charge. But remember, this decrease is only up to group up to group 17. In group 18, that is the noble gases or inert gases, there is a sudden increase in atomic size, because in noble gases the outermost shell is completely filled, so many electrons are there, and these electrons, they repel each other, because of which the size of the atom suddenly increase, right? So that is about the one important periodic property, that is the atomic radius. And you will see that many of the properties of elements, if we talk about metallic and non-metallic character, if we talk about electronegativity or electropositive character, all these factors somehow in one way or other, they depend only on atomic size. So if you keep in mind very clearly the periodic trends about the atomic size, you will be able to understand the periodicity or the trends in periodic properties of other properties also, like as I told you that metallic and non-metallic character, electropositive and electronegative character, and so on, right? So have a nice day. Goodbye.